Hi guys, I'm here atop the Eagle's Nest in Germany, about 1600 kilometers west of Chernobyl, and this information is relevant because today on Red Minerals I'm gonna look for some fallout. Let's get to it. This little spike here is the fingerprint of the Chernobyl explosion that happened 40 years ago. Here's how I found it.
Most people think that the Chernobyl disaster is history. But in South Bavaria, scientists can still find Caesium-137 today. I wanted to know whether someone like me could actually find this nuclear fallout with nothing more than a Radiacode. To do this, I traveled to the Alpine valleys around Berchtesgaden to find and analyze Caesium-137 from the Chernobyl disaster. When the number 4 reactor at Chernobyl exploded in 1986, the radioactive fallout began to spread all over Europe. It did so very unevenly though, and some areas received way more fallout than others. One of these areas struck by fallout is the forested valley around Berchtesgaden. I was curious if a relatively difficult experiment like this could be done by an average guy like me. My main plan was to hike in the affected areas while mapping radiation with the Radiacode strapped to my leg. I was on the lookout for promising hotspots and I took soil samples on the way. It did not take long to find something interesting.
So we were hiking along this trail near Berchtesgaden when I noticed this clay deposit on the side of the road, or a clay washout rather. I've read it in a study somewhere that cesium really likes to stick to clay. Right here I have about 10 CPS, and if I come here I get about 30. So I will take a soil sample from this area and hopefully in the gamma spec I can measure some Caesium-137. Let's see how it goes.
Even though the dose rate was a good sign, I wasn't sure about this sample having cesium, since a lot of other elements can also accumulate in clay. However, this was the most promising spot we found that day. With the first sample in the bag, we visited the famous Eagle's Nest. The building itself was made of granite which had elevated radiation levels. I made sure to upload this find along with my other tracks to the Radiaverse. Check it out, you can see all of my findings and tracks along with thousands of others worldwide.
So we just started a longer hike from Berchtesgaden to Ramsau, and hopefully we will find some hotspots on the way.
I've read a lot of studies on the cesium content of mushrooms in the area, so I had my eyes peeled.
So what happened is that I found some mushrooms here, forest mushrooms, and those tend to accumulate cesium. So the plan here is to pick these, dry them, and then measure them in a Marinelli beaker.
Mushrooms like to accumulate heavy metals, so they can have a higher concentration of CS-137 as well, along with the meat of wild boars that feed on mushrooms. After hiking about 20 kilometers, we visited Königssee to cool off and record some more tracks to the Radiaverse.
So you might be wondering, how can I measure Chernobyl fallout all the way out here? Let me try to explain. There are two main things to talk about when it comes to Chernobyl fallout: cesium and gamma spectroscopy. Cesium is a chemical element. It can be found in nature, but its isotope, CS-137, can only be found in nuclear reactors as a fission byproduct. It is, of course, radioactive. CS-137 has a half-life of 30 years, and since Chernobyl was 40 years ago, it can still very much be detected in contaminated areas.
A very promising spot was found near Ramsau, very close to where I found the mushrooms.
So I just found a nice little depression in the middle of absolutely nowhere. So of course I took special care not to do this in the actual national park of Berchtesgaden, but somewhere else in the forest. But still, I really don't like to disturb nature, so there's no big trees around. This is just a smaller depression of the soil, and as you can see, I'm measuring 14 CPS here, which is nothing but twice as much as I measured elsewhere. This is more than enough for me. As if I was not even here. So even though I can detect radioactivity, how do I know that it's cesium that I'm measuring? Well, that's where gamma spectroscopy comes in. If you want to do gamma spectroscopy on your own, all you need is a scintillation device like the Radiacode. So what is gamma spectroscopy? Well, in very simple terms, it's being able to tell what isotope are you detecting based on something called a gamma spectrum. So, as you can see here, I'm taking a live gamma spectrum at the moment with the Radiacode, and when I place the cesium control source on my Radiacode, you can see that there are peaks forming in the spectrum. Each isotope has its own distinctive gamma peak, cesium at 662 kV. This basically means that if I can find this peak in any of my soil samples, I can confirm the presence of CS137. And that's it.
As our stay was coming to an end, my Radiacode detected slightly increased values next to Hintersee.
Will this gonna be cesium? I'm not sure, but we will check it out.
This time I broke out the Ludlum 44.2 scintillator as well. This is an industrial grade device, but it works just the same as the Radiacode.
And currently I'm just above 1K, so about 1100 CPM. I come here to the spot that I found. As you can see, I'm slowly going up to about 2000 CPM. So twice the amount, more than twice the amount of background. So my goal is to get a sample from the top 10 or top 15 centimeters of soil, which is where cesium accumulates.
After taking my sample, I was curious if it can increase the reading on the Radiacode on its own.
So it should be more than 7.8 CPS. Let's see. It's definitely increasing. 1 or 2 CPS increase just from this small sample, and the geometry is all screwed up. So I'm really hopeful that this is gonna be cesium.
Finally, it was time to haul the goods home to analyze them. To get accurate results, I have dried my samples for a few days and then I sieved the soil samples. I also took a reference soil sample from Budapest a few weeks back. I ran a long background spectrum at the exact spot where I was gonna measure my samples, and then I measured my samples for either 24 hours or until I got to a reasonable error margin. I did this in a Marinella beaker from Radiacode. By subtracting the background from my sample spectra, I got a clean spectrum as a result. I used the Radiacode app to calculate the activity of my samples. This is measured in becquerels. I also just looked at the spectrum to check for the cesium peak. My reference from Budapest came in at 70 becquerels per kilogram with a barely visible CS137 peak. We received a small amount of fallout here, so it made sense. The first sample I found measured 3 times this amount, but unfortunately cesium was not the main source of radiation, as I could see the peaks of thorium and potassium that also like to accumulate in clay. My sample from Ramsau was a whole other story. I could clearly see the distinct cesium peak with a measured activity of 335 becquerels per kilogram. That is a significant amount of CS137 in soil. Naturally, expectations were high for the mushrooms I gathered nearby. Well, those mushrooms came in at 4 kilobecquerels per kilogram. That means that the amount of mushrooms that you can see here could literally be used as a control source. 4000 becquerels is more than 6 times the allowed limit for cesium contamination in foodstuffs. Sure, I have read that mushrooms and boar meat can still be contaminated, but this was a first-hand experience for me. This was truly the fingerprint of Chernobyl causing problems 40 years later. You have no other way of knowing this stuff unless you own a device like the Radiacode. The rest of my samples also had clear cesium peaks. This was an amazing experience, and I would like to thank Radiacode for giving me this opportunity. Stay safe guys, and see you in the next one.